mean. The mean of the averages is exactly the same. The variance of the averages is the old variance divided by n, and the new standard deviation of the averages is the old standard deviation divided by the square root of n, which right now, these formulas don't really mean a thing to you, but then on the next page I'm going to show you how to use them. The math behind this is very simple. It is exactly the same as the last section with the x minus mu over sigma, except for that instead of like sigma on the bottom, we'll be doing sigma divided by the square root of n because it'll be a just slightly different formula. Yes?
I'm confused. What's the mu and a minus?
This is an x bar right here. So this means the average of the x bars is the old average. And this one is the variance of the x bars is the old variance divided by n. And here is the standard deviation of the x bars, or the standard deviation of the means, is standard deviation divided by the square root of n.
So if it's the old one, then why do we even need to do the equation?
And because it's just telling you that these two are exactly the same. It's just telling you that they're the same, but that these ones change. So no, you don't need this equation at all, because they're exactly the same. This is just telling you that they're the same. Okay? All right. So let's flip to the second page. I'm going to show you how to use it now. It's one of the hardest things to figure out how to do. You alive, Brian?
Yeah.
Cell phone bills for residents of a city have an average of $47 and a standard deviation of 9. Can somebody tell me, why would it make sense to you that cell phone bills, if I graphed everybody's cell phone bill in Lewiston, that it probably wouldn't make a bell curve? A lot of us use the same provider. A lot of us are probably having the same price. What else?
Different family sizes with a different number of lines.
Right, so instead of having most people in the middle, I bet you would have a lot of single people over here on the low end, right? And a lot of families over here on the high end. So actually it might even look bimodal, which means there's two little bell curves going on, okay? So, and notice that this problem doesn't say that it was normal. Okay? Also notice this. See how it says standard error? That's a new word. Standard error is the standard deviation, the new formula for standard deviation. So go back to that front page and write right here. This is standard error. Okay. So cell phone bills for residents of a city have an average of 47. I'm going to write down the old mu was 47, and the standard deviation is 9. Now, I want you to imagine that I threw all of those numbers, like every single number. I went around and I asked everybody in Lewiston, and I wrote down how much they're paying on their cell phone bill, and I threw it in a big bag. Okay, so now I've got a big bag of all these numbers. Everybody understanding me? And then I started pulling out samples of 100 at a time. And I took these 100 samples, and that includes people who are paying a lot, right? And some people who are paying very little. And I took the average of those. And then I graphed all the averages. Do you see how all the averages now are probably going to make a bell curve? Central limit theorem. And now it says, find the new mean and the standard error. Well, what's the new mean the same as? The old mean. But you do have to remember that you have to write it like this. The new mean is 47. That's the mean of the means. And the new standard deviation, what was that formula in the front? What should I do to the old standard deviation to figure it out?
Standard deviation by x squared, or the number of trials.
Not quite.
Square root number.
Yes, the square root number of the trials. So it'd be, I'm going to take 9, and I'm going to divide by the square root of, what was it, 100? Because there's 100 in each sample. Which is what? 9 divided by 10? So my new standard error is 0.9. Okay, this is a very complex idea, but you guys are so smart that you can handle it, so just don't write it down. Pay attention, Ryan. Live for the moment, you're okay. Okay? Do you have a bad day today?
No.
Okay. All right, so think about it this way. Imagine that I have a big basket, okay? I've got a giant basket right here, a big garbage bag full of Post-its that say everybody's cell phone bill. Everybody with me, right? Okay, I grab a handful out, I find the average of my handful, and I start graphing them. Now, here may have been my original cell phone graph, or maybe it's even more like this a little bit, right? Like, here's what Lewiston looks like paying for cell phones. Some people are super low, some people are super high. It's not a bell curve, maybe it's got kind of 2 bumps in it, whatever, it's something, okay? But then when I take the average, if I have 50 cell phone bills in my hand, is it likely that my average would be way up here? Of just one pile? No. Would it be likely that I would happen to grab 50 tiny ones? No. So not only when I graph them, graph all my averages, does it become a bell curve, but it gets tighter. Because all my averages pull into the center. Because I've got so many of them. It's really weird. It'd be really weird for me to grab 50 people who all have really high cell phone bills, or 50 people who all have really low ones. So that's why the standard deviation shrinks. The middle number is still the same. You see, the average is still $47 here, but that standard deviation has gotten really tight because now we're taking all the averages. It's a hard thing to understand. The math is easy. Was this math hard? No, it was 9 divided by the square root of 100. But understanding where it's coming from is freaking Caitlin out. Okay, let's try again. Assuming that the training heart rates of all 20-year-old athletes are normally distributed. All right, it's already a bell curve. They have a mean of 135 beats per minute and a standard deviation of 18 beats per minute. Random samples of size 4 are drawn from this population, and the mean of each sample is determined. Can you see that this tells you it's going to be a central limit theorem kind of question, because they're taking like handfuls of samples and finding the mean now. And now we're looking at all the means. Find the mean and the standard error of the means and sketch a graph. I'm not going to sketch a graph. So my new mean, how do I find my new mean? Exactly the same. Nothing has changed. Look over there. The middle is still the middle, but now it's tighter. So now my new standard deviation is not 18 anymore. It's 18 divided by the square root of 4, how big those samples were. What's the square root of 4? 2. 18 divided by 2 is 9. So now it's a little bell curve, and it is tighter, because now I'm looking at all the averages. Yes?
So tell us how it's normally distributed, so then why do we have to do that?
Because now we're looking at all the means. So let's pick something that is normally distributed, okay? We're going to try this one more time, and I'm happy you're asking, because this is a hard thing to understand, and so far